All right, in section 10.1, we're going to talk about the limit. And to introduce the limit, we're going to start with graphically and look at what we have in this graph. This function here is the function f of x is equal to x squared minus 4 over x minus 2. What do we know about this function when x is equal to 2? Who knows what we would say about this function at this point right here? Well, about the function itself, not even about the limit. Just the function itself. What does this open circle represent? Undefined. That's right. Undefined. When a function is undefined at a certain point, it means that we can't find the y value at that point. That's what an open circle will represent on a graph. If the function were defined at a point, then the circle would either be closed, if we had a circle at all, or it would just be part of the regular function. That's what all this straight line here is. It's just function values where it is defined. If we look at the graph on the left side of x equals 2 and the graph on the right side of x equals 2, these look like they would meet at what y value? So what's the y value going in to this point where x is equal to 2? Or coming in like this. What's that y value? 1, 2, 3, 4. Exactly. That is y equals 4. It's these y values that are going to be important to us as we start talking about limits. So let's go ahead and define what a limit is, okay, and the notation. So the notation looks like this. It's LIM is the abbreviation for limit, and under that we write x goes to c, and the c is going to be some x value. We need to tell it what function we're thinking about here, and so we put the function either by name, which is f of x, or we write out the expression for the function right there where the f of x is, and we say that that is equal to L. Together, these things mean the following. This means that as x approaches c, the values of f of x approach L. And then sort of a little subnote here. And this is the important part. Even if f of x is undefined at x equals c, the limit can still exist. This is why we invented the limit. It's for functions where we have places where the function value is undefined. We still want to know what's going on with that value. And so we have the limit instead. If we look at the problem above here, then the limit as x goes to 2 of x squared minus 4 over x minus 2, that is equal to the y value, 4. And that is what is embodied in this example right here. And that's sort of how we're going to write these when we get down to them. So this is the first step, seeing what this means graphically. You are approaching a certain number on the x-axis, right, from both left and right, And if the graph approaches a single y value, that y value is called the limit. Okay? Now, we did this with a point on the function where it was undefined. We can actually do this with any point on this function, because even if the function is defined or undefined, we still try to find the limit. It's still, are we approaching certain numbers? All right. Questions? All right. Let's look at example number 2. Given the graph of function f, find the limits. I'll do the first one, and then I'll let you work with your partners on the other two. The first one here is find the limit as x goes to -2 of f of x. So we're looking on the graph as x goes to -2. And see, as we're getting close to this x value, x equals -2, do my fingers approach the same value? Yes. And what is that y value? It is 1. So that is the limit. So the limit is 1. Again, it's because we're coming in, we're approaching the same y value. Even though the function is undefined, we still get that same y value. All right, go ahead and work examples 2, part B and C with your partner. Okay, let's call on some people. Let's see. Carla, what did you get for part B? 0. Very good. So as x goes to 1, right, this is the x value. As x goes to 1, the y values go to 0. That's the y value of the x-axis. All right, and Daniel, Messina? Where's Daniel? 2. Where's Daniel? There you are. The limit as x goes to 3 of f of x is 2. Let's check that out. Here's 3. So we're going into this point right here. It is defined. And so it is 2. All right, questions over those? The place where people get sort of confused on limits at the very beginning is you have to make the distinction between the x's and the y's. The x value is written under the limit. Okay, so you're always going to that. It's then a matter of how high or low is the graph going at that moment. All right, so that was sort of a graphical look at limits. We can also sort of look at them numerically, and then we're going to make sort of leaps of faith whenever we do this. If you have your calculator, go ahead and type in this function into y1. The function is x cubed minus x squared minus 9x plus 9 over x minus 1. Be sure to use parentheses around the numerator and the denominator. Okay. I'm going to demonstrate it on my calculator here. And I activate the document camera. Autofocus. There it is. So we have x cubed minus x squared minus 9x plus 9 divided by x minus 1. All right, now once you get the function typed into the calculator, we're going to create a table of values. If you have the printed sheet, you know which values we want to use. You also can see that those values, they don't increment at the same pace, right? One of them goes up by 0.09 and the next one 0.09, all that sort of stuff. What we need to do is we need to set up our table. To set up your table, do second and then table set. Table set is above window. And what we're going to change here is where it says independent, we're going to change that to ask. When you change independent to ask, you are telling the calculator that you are going to supply it with the x values. Next, go into table. So that's second table. Table is above the graph button. And we have an empty table. Now, based on the table presented here, we want the value at 0.9. We put our function into y1, and so we know that the value of the function at 0.9 is negative 8.19. All right, go ahead and fill in the rest of your table here with these values, with 0.99, 0.0999. We don't want to put in 1 for 1 because there was a term of x minus 1 in the denominator, which is going to give an error. That's why the table says undefined. The function value is undefined at that point. And then keep going. Fill in your table. And then what I want you to do is to make a guess about what the limit would be as x goes to 1. Even though the function value at x equals 1 is undefined, we can still make a very good guess about what the limit would be, as long as it approaches the same number from both sides. So go ahead and do that with your partner. I'll come around to help. Oh, you need to change it to task. Okay. Task. And now here. You got some extra stuff. Just type it. Okay. All right, anytime. Anytime. You got it? Okay. Let me fill in the chart here. All right, so what do we believe the limit is? What value, what y value does the chart suggest we are approaching on both sides of x equals 1? What is it? Tell me. Negative 8, that's right. So negative 8 is going to be our answer. Now, how do we write that? Well, we want to tell it we're doing a limit, so it's limit. And then what x value are we going to? 1, so that's x goes to 1. We want to give it the function. Here, I'm going to go ahead and write out the name. This way we know exactly what's going on. And then this is equal to negative 8. Exactly. Now this isn't concrete proof, but we are learning about how the functions work, and we could do some stuff algebraically to show that this is actually the correct answer. Question?
Can you just write limit and then put like f of x? Or do you have to?
You could have just put f of x. But you do have to put it in the x minus 1 though. You did put that in, right?
I really.
Yes. Yeah. Yeah. You have to be sure to tell it where the limit is going on the x's, because there's limits all over the place. Okay. Go ahead and do the next one with your partner. And actually, there's 2 to do. So go ahead and do the next 2 with your partner. If you don't have a calculator, look on with someone that does. The first one works out really nice. The one on the next page, you're going to have to make an educated guess. The answer is a fraction. So figure out what fraction that's going to be. Anyone want to know the donut? We have. Looks like I overwrought on the donut. Hang on. All right. Now does anyone else want a donut? We got so much sugar. You want a donut? This is the very cream way.
So how's the snack thing going to work? You take turns bringing snacks.
Did y'all sign the snack thing? Is that something you're interested in or not? I don't know if you're interested in it or not. I just thought you know.
Bag of chips, or we bring it back?
You bring back a chips, but if you bring back a chips, we got some like little bowls. There were 36 people. Yeah, I don't want to break anybody or put somebody in financial despair because of the thing. But I thought you. Okay, y'all need me to go to the next page? Let's do the next function. All right, here comes the next function. Ooh, that's a big old function. Look at that. Okay. I think you should get these answers here. Are these what you got? All right, everybody get these table values here? And so what is your guess? Yeah, the limit as x goes to 3 of, well, I don't want to say f of x here. We don't know that it's f of x. I'll just have to write it out. It doesn't say that it's f of x, but it is a 1. So you should have got a 1 for this one. All right. And let's look at example 5. I got 0.3176, 0.3318, 0.3317, 0.3335, 0.3349, and 0.3494. So the limit as x goes to 2 of x cubed plus x squared minus 2x minus 8 over x squared plus 38x minus 80. What do you think that one's equal to? What fraction?
1/3.
Yeah, that's 1/3. Yeah. So maybe you remember that the fraction 1/3 is written as a decimal is just 0.3333. Now, there's no way to know that that's exactly based on this, but this is, I sort of led you in the right direction. So that's the first part of this. So now we've done it graphically and we've done it numerically. We've looked at the graph to see that a limit exists when we have the two lines coming into the same one. And now we have the table, meaning the two sides of the x, the y values come into the same one. Let's see if we can do the same thing on this next one. Example 6. F of x is equal to the absolute value of x over x itself. What is the limit as x goes to 0, the absolute value of x over x? So, let's create a table. We'll have x's and f of x. And 0 is our middle point. And notice that we have x in the denominator by itself. Remember, one of these fundamental rules of algebra is you cannot divide by 0. Well, since it's x alone in the denominator, when x is equal to 0, that's division by 0. So we can't do that. So here this would be undefined. All right. That's okay. Even if it's undefined, we can still try to find the limit. No problem. Now we're going to have to go a little bit to the left of 0 on the number line. So that would be negative 0.1, and then work our way into 0. So then a little bit closer to 0, negative 0.01, and then a little bit more, negative 0.001. And then I'm going to use those same symmetric values, but the positive versions on the other side here. So 0.001, 0.01, and 0.1. Does everyone see that these numbers are in fact in order from least to greatest? The more zeros I have here, the closer I'm getting to 0, and then the fewer I have here, the further away I'm getting to 0. All right. We need to compute these values. So let me go ahead and do that in the calculator. There it is. And I'm going to do absolute value. So that's math number ABS x, close parentheses, divided by x. So absolute value again was under math and then number. All right. Let me go into the table and clear these out. Can I clear them out? Yeah. I hit delete, clear them all out. And let me type these in. So negative 0.1 is negative 1. negative 0.01 is also negative 1. Negative 0.001 is negative 1. They're all negative 1. Are they all going to be negative 1? Are they? Let's try. 0.001 is, that one is positive 1. 0.01 is positive 1. And 0.1 is also positive 1. Oh, so some of them were negative 1. And some of them were positive 1. Looking at the chart, are we getting closer and closer to the same value? Are we getting closer to 0?
Staying at negative 1.
Yeah. You sort of think that we're getting closer to 0 because 0 is in the middle. But we're actually not. Pretty much anything to the left of 0 is going to give me negative 1. All of these are going to be negative 1 for any value I choose less than 0. And any value I choose bigger than 0 is going to be positive 1. There's no movement towards 0. It's either negative 1 or it's positive 1, and there's none of this that we need for the limit to exist. They're all separated. And now I forget which movie this is. It's one of these Lohan movies, right? You know Lindsay Lohan, I think, right? She says this, right? The limit as x goes to 0 and the absolute value of x over x. Since these are not moving toward the same value, what do we say? The limit does not exist. And that is abbreviated DNE. The limit does not exist. Okay. Now, I want to show you some more about this function so that you can see why it doesn't exist. To do such, I need to remind you about what the absolute value function is. So let me call that f. Okay. You have been told all your life that to take the absolute value of something, you just make it positive, right? Just make it positive. It's like magic. Make it positive, right? You have to come up with some algebra behind all that. The algebra behind the absolute value function is what we call a piecewise function. A piecewise function is a function that uses one expression for certain values of x and a different expression for different values of x. Okay? The split point for this piecewise function is when x is greater than 0 and if x is less than 0. Okay? Now, what I want you to think about is the action that you take on the number when you take absolute value. Okay? So, for example, what is the absolute value of 3? 3. What did you do to the 3? Nothing. What's the absolute value of 7? 7. What did you do to the 7? Nothing. Right? So if, and those two numbers were positive. So if x is positive, right? Positive means greater than 0. What do you do to the x in order to get the absolute value of x? Nothing. So the absolute value of x, when x is positive, is just x. It's just whatever that number is. Okay? All right. Now, what if x is negative? What is the absolute value of negative 5? Positive 5. What is the absolute value of negative 8? Positive 8. What did you do to the negative 5? And what did you do to the negative 8?
Multiplied by negative 1.
Multiplied by negative 1. Very good. So, to change a negative number under absolute value, you multiply it by negative 1. So that is negative x. Right? It's negative 1 times x. So, just to demonstrate, let's do it this way. What is the absolute value of negative 5? By definition, that is the negative of negative 5, which is positive 5. And that's what's happening. Anytime you take the absolute value of a negative number, you must multiply it by a negative, which will cancel that negative out and give you a positive. That's the action that you're doing, right? We've simplified it from 8th grade and beyond. So, just make it positive. Just make it positive. It's fine. It doesn't work with variables because you don't know if your variables are positive or negative unless you start denoting things like this. Now we do. All right, so that's the definition of absolute value. Let's go back to the function that we have, which is the absolute value of x over x. I'm going to rewrite this as a piecewise function. So that would be x over x if the x is greater than 0, and negative x over x if the x is negative. Notice I just take the piecewise definition and replace where it said absolute value of x over this x right here. All right. What is x divided by x? That's 1. And what's negative x divided by x? Negative 1. Well, that's where our 1 and negative 1 came from. It's the x over x or negative x over x. Now, I didn't put in x equals 0, and I left that off on purpose. There's only one place where we can put it, and that is right here. If x is equal to 0, the absolute value is 0 itself. Because in the second step we start dividing by x, now we can't even consider x equals 0. So that's okay. We're good. Well, there you go. There's how you make your little table. If the x's are positive, they go to 1. If the x's are negative, they go to negative 1. They never move toward a central number, therefore the limit does not exist. The graph looks like the following. For anything where x is positive, the value is 1. So here's all these positive numbers. And it's a straight line over to 1. Now, it doesn't quite connect, and the function is undefined at 0, so we have to put in an open circle. Same thing on the bottom. Where the x's are negative, on the left side of the graph, we end up with y is equal to negative 1. And we have an open circle there as well. Again, the limit exists if I can connect the 2 points, right? Well, here I can. The fingers are spread apart. There's no movement toward the center. The limit does not exist. That's limits, right? Either they exist, 2 fingers come together, or they don't exist. If they do exist, the limit does exist, then it exists, and the value is whatever that y value is, where they range together. Okay. So the limit does not exist, and that's sort of a shame. What could we do that we could get some information off of this deal? The answer comes to us in the form of this next piece, which is called a one-sided limit. Okay. And it's exactly what it says. It's a limit from a particular side. So here we have the 2 parts here. We have the limit from the left. The notation for the limit from the left changes a little bit. We have the limit as x goes to c, and then as a superscript right here, we put a little minus sign. So it's x goes to c from the left of a function f of x, and we say, let's call that one L1. And what this is telling me is the following 2 things. That the x's that we can consider when we do this, what I sometimes call the left limit, the limit from the left, is we can only consider values of x that are smaller than the number we're going to. And we are still going to see. but we're only considering the values that are less than it. So let's suppose that there's a graph, there's x equals c, and the graph comes in on the left side like this. Then, if this limit exists, then it would be L1. What we have is we are considering only the left side of the graph when we're doing the left limit. We don't care what goes on the right side. We don't even know. It doesn't even matter. Okay. In addition to the left limit, we also have the right limit. So the limit from the right. How do you think the notation changes?
Plus.
Yeah, we're going to use the limit as x goes to c with a superscript of a plus. And we'll call this one L2. And of course this means that the x's we consider are bigger than c while still going towards c. So there it is, maybe, something like that. And it's L2. So it's just a matter of looking at the graph coming in from the left for the left limit and from the right for the right limit. The last thing we need to talk about today is the existence of limit. And this is the whole limit. Okay? And this is the following. The two-sided limit, I put that in parentheses because we rarely call it that. We call it that if we need emphasis. Otherwise, it's just the limit. Okay. The two-sided limit exists if and only if the limit from the left and the limit from the right both exist and are equal. In symbols, we have the limit as x goes to c of f of x is equal to L implies, both ways, the limit as x goes to c from the left of the function f of x is equal to L, which is also equal to the limit as x goes to c from the right of f of x. And let me just finish this problem here. Back to that same function, the absolute value of x over x. The limit as x goes to 0 from the right side, we discovered that that was 1 based on the graph that we had before, right, which looked like this. Right? If we come in from the right, the y value is positive 1. If we come in from the left, the value is negative 1. The two one-sided limits exist, but they are not equal. Since they are not equal, the whole limit does not exist. Let's go ahead and check these. It's going to be hard for me to show the screen and write in the answer, so I'll let you look on your page for the graph itself. What did you get for E? Go ahead, in the corner.
2.
2. Yeah. And F? Next. 1. G? Does not exist. Yeah. Since these two are not the same, then the full limit does not exist. And what was the actual function value? -1, right? That was the tricky one, right? That's down here. It's down there. So the point where it's the function value doesn't even have to be one of the anchor points for one of the one-sided limits. It could just be something entirely else. All right, and the next one here, let's see. I, what'd you get for I? Right here. Go ahead. Yeah. 2. And
You go to the left.
what about someone else? Jay?
2.
2. Next. What'd you get? 2. Yeah. And 2. They're all 2s, right? They're all 2s. We're going to talk about this later in the week. This is a property of a function called continuity. The limit exists, the function value exists, and they're both the same value. So we'll do a whole section on that later on. All right. What about M? Right here. Right. Yeah. 0, and 0. Right. Next. Right. 0. And the last one is 0 as well. Yeah. Now this one didn't have any like a given point, but it was part of the curve. Just being part of the curve is a point in and of itself, right? We use the bigger version of the dots and everything to represent sort of endpoints. Any questions over that one? All right. Let's look at properties of limits. Now, this is leading us into doing the algebra behind some of these limits. I'm going to draw some of these out for you, and then we'll just sort of assume that the rest of them work as well. Here, if we have an f or a g, those are going to be functions. The c and the k are going to be real numbers, constants, and n will be a positive integer, 1, 2, 3, etc. Okay. We have these 9 properties. The first one is that if you take the limit as x goes to c of a constant k, then the result of that limit is that constant number. All right. So let me draw this one out for you. If you have a graph and you have the function y equals k, that is a horizontal line. And it is a horizontal line where y is equal to k. Let's put it right there maybe. The x is going to c, so I'm just going to pick some c value that's on the x-axis. And we're going to look at this point right here. That is the function value above c. If we want to do a limit, we have to come in from the left and from the right. If you come in from the left, the y value you get to is k. If you come in from the right, the y value you get to is also k. So the two left and right side limits are both k. So the whole limit is k. In other words, there's nothing else going on but the value k. And then that's it. On number 2, we have the limit as x goes to c of the function x is equal to c. I'll draw this. This is y is equal to x. You remember that is this line, 45-degree angle line, like so. We'll pick an x value, c, and go up to this point here. What is the corresponding y coordinate for that point? Yeah, it's c, right? Because the graph is y equals x is equal to c, so y is equal to c. When you do the limits, you're coming in from the right side, you're coming in from the left side, and then what y value do you approach coming in from left and right? C. So there it is. Okay. These are the basic building blocks for doing limits. The next ones I'll just sort of talk about the properties of these limits. Property number 3 says the limit as x goes to c of k times a function f of x. That is equal to k times the value of the limit x goes to c of f. In other words, if you have a constant being multiplied by a function, and you take the limit as x goes to c, that is the same thing as finding the limit as x goes to c of the function by itself, and then multiplying that result by the constant k. So you can multiply the constant k before or after. It does not matter. Example 4, 5, and 6 are when you take the limit of two functions and you either add them, subtract them, or multiply them. Here you're taking the limit of the sum of two functions. That turns out to be the sum of the two individual limits. So you can sort of take the limit of each individual function and then add them up, or subtract them, or multiply them. Okay? So in other words, limits split up functions that are added, subtracted, or multiplied. A limit will also split up a new function that's been divided, f divided by g, as long as the limit in the bottom doesn't equal 0. Remember, this is one of the rules that we have. You cannot divide by 0. So as long as it doesn't equal 0 in the bottom, we're okay. In number 8, we have the limit as x goes to c of a function raised to a power, n. That is equal to the limit of that function, then raised to the power. In other words, I can exchange the order of the limit and the exponent. Here, the exponent is being done first, and then the limit. On the right side, it's the limit first, and then the power. And number 9 is similar. It's a nth root, and you can move the limit inside the nth root as long as what's inside is positive if the root is an even root, like a square root, fourth root, sixth root, etc. Yeah.
How will we write out the answer? 5 or 4 through 9?
I'll show you. That's example number 8, actually. So use the properties above to find this limit. So it's the limit as x goes to 3 of 2x squared plus 5x. Right? Uh-oh. Oh, we're back. Okay. So what we want to do here is use each of these. So the first thing that I notice is I can see two different functions that make up the function I'm taking the limit of. I see 2x squared plus 5x. And property number 4 said that if I have the sum of two functions, then I can split those up and take the limit of those individually. So this would be equal to the limit as x goes to 3 of 2x squared plus the limit as x goes to 3 of 5x. And we're going to justify each of these. That's number 4. Okay. So in this example, the 2x squared acts like the f from the property, and the 5x acts like the g. Next, I see that both of these have a coefficient. And we have a property that says I can move the coefficient from inside where the function is to outside of the limit. Which property is that? That is property number 3, right? So property number 3, go back and look at that. The limit as x goes to c of k times f is equal to k times the limit as x goes to c of f. So here, that means this 2 can come out in front and multiply. And also here, this 5 can come out in front and multiply. And that was property number 3. Questions so far? All right, next we have on this left side, we have x squared. We have a property that says I can take an exponent from inside with a function to outside of the limit. Which property is that? That is property number 8. Yes. So it's the limit as x goes to 3 of x squared. Property number 8. Now we're to the heart of this. What is the limit as x goes to 3 of x? It's 3. Which property is that?
2.
That's property number 2, right? Property number 2 says the limit as x goes to 3, or x goes to anything of x, is whatever that number is. So here, this is going to go to 3. And it goes to 3 over here as well. That was property number 2. And finally, we work it out, and the answer is 33. What this example is designed to do is to show you how all of the properties of limits work together. We can split up addition, subtraction, multiplication, and division. We can move out powers. We can move out constant multiples. And we can make substitutions. Now, I don't need you to memorize the properties verbatim. I need you to understand how the properties work. Okay? Practically, what you will do, you won't be doing problems that look like this. This is just an example to show you how the properties work. What do you actually do when you see a problem like this? You just plug it in. You plug in, as x goes to 3, you plug in 3 for x. If you can, legally. And that's how you will do that. What allows you to just plug it in are those 9 properties. Okay? You plugging this in, evaluating it, is the embodiment of using all 9 properties in conjunction appropriately. All right? All right, questions over this example? Yeah.
Is there going to be any questions on the test where we can't plug it in like that?
Yes. Yeah, most of them will be that way. We'll get to the ones that have holes in them and asymptotes and things like that. Yeah, definitely. All right, let's take a look at example 9. Now this one we do want to sort of write out some stuff here. And use the properties so that we can see everything. On example 9, you are given the following 2 pieces of information. You are given that the limit as x goes to 1 of the function f is 4, and the limit as x goes to 1 of g of x is negative 7. And suppose we create this new function f plus g. We don't know the expression. We don't know anything else about it. But we can still solve this problem. We can find the limit as x goes to 1. We would use one of those properties to split this up. And this would split up as the limit as x goes to 1 of f of x plus the limit as x goes to 1 of g of x. And then we would substitute the 2 given values that we had. The limit as x goes to 1 of f is 4. And the limit as x goes to 1 of g was negative 7. That gives us a result of negative 3. On part B, we would do the same thing. Let's say the limit as x goes to 1 of 6 square roots of f of x minus the limit as x goes to 1 of g of x squared using property, what number was that, 5 I believe, where we split up a subtraction. Next, I can move the 6 out to the front. That's on the left side. On the right side, we have g squared. I can move the limit inside the square. I'll do one more thing before I evaluate, and that is move the limit inside the square root. And then we evaluate. The limit as x goes to 1 of f of x was 4. And the limit as x goes to 1 of g of x was 2. Was negative 7. And then that's squared. And if you work all that out, you get negative 37. Questions? Again, all you're doing is whittling into the function to get to where it's the limit as x goes to a number of the function itself, or an x, depending on which one you're doing. But as we mentioned earlier, most of the problems that we'll be doing are...
I asked if they switched it back and they did.
Oh, good. Are of this next type, the solving limits using algebra. Okay. So before I go on, any questions? Okay. This is where it gets real right here. This is the good stuff. This is the one. Example 10. Compute the limit. This is the limit as x goes to 2 of x squared minus 4 over x minus 2. Your first step when you try to do a limit is try to evaluate. See if you can plug in the x. If you try to plug in x equals 2, notice that the value of the denominator is 0. You cannot solve it when it's a 0 in the denominator. Okay? Now, the good news, however, is what's the value of the numerator? It is also 0. 2 squared minus 4 is 4 minus 4 is 0. Now, you can't cancel zeros and get 1. That doesn't work. 0 divided by 0 is something we call indeterminate. Basically, that means we can't find the value of whatever that is exactly. We need the other pieces of the function to figure out what value it could be. Okay? So the way you work these is the following. You need to factor x squared minus 4 what cancels? X what? X minus 2. X minus 2 cancels. That leaves me with the limit as x goes to 2 of x plus 2. And now you have a function that doesn't have a denominator, so you can evaluate it in this function. So this is 2 plus 2, and this is equal to 4. And that is the answer. remember, this was the first problem that we did. That was this problem right here on the first page. This is what the graph of x squared minus 4 over x minus 2 looks like. If you were to think of this as a line, what line would this be? It has a y-intercept of 2. Right? It has a y-intercept of 2 and the slope of 1. Yeah, that is exactly x plus 2. Except for one place. And that's where the hole is. X plus 2 doesn't have any holes. X plus 2 is continuous. It has everything. So this function and x plus 2 are almost alike. Almost. There's one point where they differ. Now, what is going on is that the limit is using the function values that are not equal to x equal 2. The limit is based entirely on what the other function values around it trend to. And those function values can come from x plus 2. We know that x plus 2, if the x is equal to 2, gives me this 4 that we have. And that's why we're allowed to substitute that function in for the original x squared minus 4 over x minus 2. These two functions have exactly the same values, except when x is equal to 2, which is a value that we don't care about when we are taking a limit. We use the other function to produce whatever function value that is. Okay? So that is essentially what's going on. When you canceled off the x minus 2, the only thing you did was add back in that point. And that allowed us to sort of use algebra to come up with the rest of the question, the rest of the answer. All right, let's see another example. All right. So the limit as x goes to negative 1 of x squared minus x minus 2 over x squared minus 1. Notice that if you try to plug in negative 1, you get a 0 in the denominator. That tells you you need to try to factor. So this one will factor as the limit as x goes to negative 1. How does the numerator factor? And how does the denominator factor? We're going to have x minus 2 and x plus 1. We're going to have x minus 1 and x plus 1. It's the difference of two squares. The x plus 1 term, those cancel. And in fact, the x plus 1 term is the term that's causing all the problems. We have to get rid of the 0 in the denominator. If we are taking x as x goes to negative 1, then the term that would cause a 0 would be x plus 1. That's the one we got to get rid of, and bingo, there it is. It's gone. Now I can work with this, and I can plug it in. It's going to be negative 1 minus 2 over negative 1 minus 1. Negative 3 over negative 2, which is 3/2. It comes from, so a limit, you have to have two pieces to do a limit. You have to have a function that you want to do it with, and you have to have what x value along the x-axis you want to take the limit to. Yeah. All right. Let's take a look at example 12. This is the limit as x goes to 0 of x to the 7th minus 4x cubed over x to the fourth plus 2x. What should we factor from the numerator? How many x's can be factored from x to the seventh minus 4x cubed? X to what power?
3.
Yeah. You can factor out x cubed. If you're looking at two of them here, you have x to the seventh and x cubed. You can always factor out the smaller exponent of x's. So that would be x to the fourth minus 4 over, and then how many x's can we factor from the denominator?
1.
Yeah, x to the first, and this is x cubed plus 2. When we cancel here, we get x cubed on top and x on the bottom. Those cancel and give me x squared on the top. So that one completely cancels. This one somewhat cancels and gives me a 2. It leaves me with x squared times x to the fourth minus 4 over x cubed plus 2. Can you plug in x equals 0 without getting a 0 in the denominator? Yes. Since you can, you do so. And this would be 0 squared times 0 to the fourth minus 4 over 0 cubed plus 2. 0 times all that is still going to be 0, which is okay. That's fine. All right, questions? All right, we'll do some group work later where we practice more of those types. Let's look at a different type of problem. Suppose you're given a function, f of x, and then some quantity involving that function with a limit. We'll be doing more of these toward the end of the week. This is a very special thing called the difference quotient, and that leads us into the derivative. But this is the limit as h goes to 0. So it doesn't have to be x. It could be, whatever, h. And the function that we need to take the limit of is f of 3 plus h minus f of 3 over h. So first thing I want to do is remind you what f of 3 plus h means. You are taking the quantity 3 plus h and you are plugging that in to the function. The function is the squaring function. So that means take 3 plus h and square it. And we're only squaring it because it's the squaring function. If it were some other function like, square root of x minus 4x, then you would put in 3 plus h every place there was an x. That's the first thing I need to remind you of. The second piece is that whenever you square a binomial, right? Binomial means it has two terms. When you square it, you end up with 3 pieces. A lot of people only do the first one and the last one, and you forget the middle piece. Let me show you a trick on how to do the squaring of a binomial. You square the first term, you get 9. You square the last term, that's the h, so you get h squared. And then in the middle, you get the first term times the last term times the 2. So 3 times h times 2 is 6h. Okay. Only works with squaring, doesn't work with cubes or fourth powers or anything else. But it does work with squaring. Okay. All right. So with that little piece of knowledge, let's go and compute what we're actually here for. The limit as h goes to 0 of f of 3 plus h minus f of 3 over h. This would be the limit as h goes to 0, 9 plus 6h plus h squared, minus, the next piece is f of 3. That means we need to take 3, plug it into the function. This function is the squaring function. What is 3 squared? That is 9 over h. What cancels from the numerator? The 9's cancel. That leaves me with the limit as h goes to 0 of 6h plus h squared over h. Can I plug in h equals 0? No, because you get a 0 in the denominator. So we need to do something else. What does it look like we need to do? Yeah. Notice that both terms in the numerator have an h. I can factor out the h and cancel. So we have the limit. The limit as h goes to 0. H times 6 plus h over h. Cancel the h's. That leaves me with the limit as h goes to 0 of 6 plus h. There's no more denominator, so I could plug in the 0. Questions? Okay. Something I want you to notice about the way these things are being written. I am always writing limit as x goes to whatever or h goes to whatever until I actually make the evaluation. That is the proper way to do it. It's always the limit as h goes to 0, 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 and then no more limit, because when you substitute h equals 0 in for this h, that is you doing the limit. These limit, those are the commands. Say, you need to do the limit. You need to do the limit, and then when you do the limit, then you've done it, so you don't write it anymore. Okay? So you always write the limit until you get to that point. Okay. Example 14. In this one, we have a piecewise function. F of x is equal to the function x squared plus 1 if the x is greater than or equal to 0, and it's equal to negative x plus 1 if the x is less than 0. We want to know the limit as x goes to 0 of f of x. Now, the problem here is that we have two different pieces, and those pieces split up over at the x value that we're trying to compute the limit of. So the trick to doing this is to compute the individual one-sided limits and then use our rule from before. If the one-sided limits are the same, then we know what the full limit is. If they differ, then the limit does not exist. All right? So let's do the right limit first. So it's the limit as x goes to 0 from the right of f of x. Now the question is, which expression do I use if I'm doing the right limit? Is it the x squared plus 1, or is it the negative x plus 1? And how do you know? X squared plus 1, because you're coming from the right, and greater than 0. Greater than 0 is the right side of 0, right? So notice how we're using these inequalities to show me what side of the value you're on. If it's the right side, then it must be greater than a number. If it is the left side, it must be less than the number. So this is the limit as x goes to 0 from the right of x squared plus 1. Any denominators? No fractions, so we just plug it in. And we get 0 squared plus 1 is equal to 1. Okay, that's one piece of the answer. Next, we want the limit as x goes to 0 from the left of f of x. Same logic applies. You look at the piecewise function and determine what expression is being used with numbers that are less than 0, and that is the negative x plus 1 expression. There are no denominators, no problems. Plug it in, and we get a 1. What is your conclusion, thus, about the limit as x goes to 0 of f of x? It's 1. Yeah, these two are the same, which gives me a 1. In fact, if you look at the graph of this, the right graph is the parabola at moved up 1, and it's only half of it, so it's semi-parabolic, so it looks like that. On the left half, it's a line with slope -1 with a y-intercept of 1. And so sure enough, these two pieces meet, and they meet at 1.